In this video, one will be able to calculate the value of capacitance as required or design the value of capacitance to improve the power factor. So I am Mohan BS, working as assistant professor in Department of EEE SJBIT. So before we proceed to the experiment or the theoretical calculation, let us understand a few basic concepts of power factor and its improvisations or corrections.
Here let us see some techniques with respect to power factor improvement. So here I have shown you an inductive circuit. That means I have a resistance and inductor in series. Let's understand its vector diagram. So voltage I am considering on x-axis, and the most important thing, we say power factor is lagging, leading or unity, taking what as reference. I want you to go through the previous video that I have shared and see what is taken as reference to say that it is lagging power factor or leading power factor. So we always take voltage as reference. So we take voltage as reference, and when we say the power factor is lagging, we simply write the vector diagram as V and current I. When you say leading power factor, again we take voltage as reference and we write current on positive I axis. Okay, so we do not take current as a reference, we just take voltage as reference. So I want you to remember this. So now voltage as reference, the current is lagging by some angle, because it's not pure inductance, it is not lagging by -90. Since it has some resistance, we do not know, just let us assume by some angle it lags. We take that angle as θ1 or phi1. Now if I introduce a capacitance in the circuit, what will happen? Now you can see I, this I is the current supplied from the source, and also it is the current consumed by your appliance. Now I want you to observe the difference. The current I is still saying it is the current I supply, the current I is now is consumed, but what is supplied? The current supplied is I dash, and we have one more current called IC. Let's understand some concepts based on this circuit now. So current I is a current consumed, current I, and in the first case, this is your, in the first case, you had only R and L. Second case, you have both R, L and C, right, trying to compensate. And in both cases, current I is what? Current consumed by your appliance. In first case, current I consumed and current supplied is the same. In second case, it is changed. So let's understand what is changed here and what is current IC. Now this is a current IC, and we know it's a pure capacitance. There's no resistance in series, right? And it's parallel to your supply voltage. And for pure capacitance, it will lead your voltage by 90 degrees. Correct? So then what will happen? Can you see what is happening? Now that much amount of reactive component will be compensated. I repeat, that amount of the whatever is the value of IC, whatever is your magnitude of IC, that magnitude of reactive power will be compensated. In the sense, it will try to pull your current I upwards. That current is I dash. Okay, so I dash is the current actually supplied from the source. So what was your current earlier? So this was your current earlier supplied from the source. As in case 1, I, what is I? Or case 2, what is I? It is current consumed. Correct? I is current consumed. But in first case, the current I is actually supplied is also true. Right? The current supplied is also I, current consumed is also I. Now when I introduce capacitance, the capacitive current will lead your voltage, then it will pull your reactive current upwards, and that is I dash. So I becomes I dash. So what is I? So current I is what is being supplied, and now the new current supplied is I dash. But remember, the current consumed is also I. So still it will consume I. So the reactive component, instead of taking from the grid, it is taking from capacitance. And now because of capacitance, you can see the total supply current angle is reduced. Right? The red color or phi2 is your new angle with respect to supply. But phi1, now don't get confused, phi1 is actually the current supplied from case 1, or at both the cases it is current consumed by a load. So current consumed by the load, it is still phi 1, but the current supplied angle becomes phi 2 when I introduce capacitance, right? So you can see the characteristics of the load cannot be changed. It can be altered with respect to supply side. So supply angle in first case, so this is your supply angle, right? The angle with respect to your supply current is phi 1. Now when I introduce capacitance, the supply angle instead of being phi 1 is now phi 2, is what I am trying to say. But the angle with respect to the load, it is still phi 1. That you cannot change. You can only alter the supply angle with respect to supply. The angle with respect to your supply. Now the current I dash after power factor correction is lesser than the original current I. I hope all would agree with this. The circuit current I dash after power factor correction is lesser than the original current I. The active or wattful component remains same before and after power factor correction, right? So you can see if you draw a line here, right? So this entire thing, give me a moment. Yes, this entire thing is actually your active component, and this is same, unaltered. That is I cos theta 1 or I cos phi 1 is equal to I dash cos phi 2. So this is not changed, is what we can observe, right? Next, this one, as you can see, this arrow is nothing but your I cos theta 1 or I dash cos theta 1, theta or 5, it is still same. Now this red color is actually your reactive component. Is it changed, or what can we decipher from this? Let's understand. Now the entire thing is actually I sin theta 1 or I sin phi 1. Now this blue color is only I dash theta 2. Now after power factor correction, you can see the value of I cos I sin theta 1 is reduced with respect to your supply side. Now kindly understand here. Case 1, what is I? I is actually current supplied as well as current consumed. Let's understand with respect to current supplied, not with respect to the load side. So current supplied is the reactive component. The reactive current supplied is I sin theta 1. After compensation, that reduces to I dash, that is I dash theta 2, right? So we can say that the lagging reactive component is reduced after power factor improvement. I repeat, that is here. And what is that? That is I dash sin theta 2. So I dash sin theta 2 is nothing but I sin theta 1 minus IC, right? So this current is actually your IC current, right? So we are subtracting. So this entire line is your I sin theta 1. In that I am subtracting IC. Then this current is your I dash sin theta 2. So I cos theta 1 is equal to I dash theta 2. So the active component remains unchanged due to power factor improvement. And when we multiply voltages on both the sides, the above equation, we get V I dash sin theta 2 is equal to Vi sin theta 1 minus VIC, or Vi cos theta 1 is equal to Vi dash cos theta 2. Now the net kVAR after power factor correction is equal to lagging kVAR before power factor correction minus leading kVAR of the equipment, right? So the net kVAR after power factor correction, what is the total kVAR after power factor correction? Lagging kVAR before power factor correction minus leading kVAR of the equipment.
So let's see the problem. The three-phase impedance coil having a resistance of 20 and 15 ohm reactance. They're connected in star fashion. They've given voltage 400 volts, three-phase supply, frequency. You have to calculate the line current, power factor, and the value of C such that the power factor is improved to 0.95. So we have three-phase supply RYB. So whenever they've given on the supply side, always it will be your line voltage, and if it is phase voltage, they would mention it explicitly as the phase voltage is XYZ value, or else by default it is always known as it is line voltage. Hence the given is line voltage. And we have a three-phase circuit that is connected in star fashion. As they have mentioned here, the load side it is connected in star, and each have a value of 20 plus 15 I. So they have mentioned here the reactance is 15 ohms, thus it is 15 I. So R connected to loads, and this voltage is line voltage that is mentioned as 400, and between any one line to the neutral is known as phase voltage. The formula is given as line voltage by root 3, that is 400 by root 3. We get the value as 230.94 volts. So this is the diagram which is not given. You have to draw it based on the given problem. So this current is called as line current. So in star connected network, as we are aware, that IL is equal to IP. So this is the current coming out from the supply is called as line current. The current entering the particular phase is called as phase current. So current entering to the red phase or B phase or Y, here current consumed by the load is called as phase current, and here in star both are same. So let us expand some equations from the power triangle that we have seen in the earlier. So the active component in watts or kW, it is nothing but OA that we have seen. It does not change. It remains constant before and after power factor correction, which is known as VI cos phi. The reactive component is VI sin phi, and the apparent component OB is called as VI. So that's the total power or apparent power in AC expressed as per Pythagoras theorem. We are aware of this equation. OB square is equal to OA square plus AB square, and representing with those units. We know the power factor correction is defined as angle between voltage or current, or it is P by Q. That is P, it is KW, P by S, P by S, which is K, that is VA. So we can rewrite this as cos phi is equal to KW by KVA, or KVA is also equal to KW by cos phi. Now taking from this equation, that is we know that AB is equal to VI sin phi, right? We can also write this as KVAR is equal to KVA into sin phi, as VI is nothing but KVA here, right? So we can substitute the value of KVA from this equation. We know that is KW by cos phi, thus we can rewrite this as KVAR is equal to KW into tan theta. Okay, so we will be using this formula in order to find out the value of capacitance. So P remains same. This is your apparent power. This is your total VR consumed before power factor correction, and this is the angle. This is the power factor for the given circuit. So we'll see how do we find the power factor. The improved power factor is 0.95. So this is the improved power factor. As you can see, the power factor is improved, the apparent power reduces, that is the current supplied from the grid is reduced, but the required VAR is always same. So the required VAR is supplied from the capacitive bank that we have connected. So VP, phase voltage, is 400 by root 3. The answer is 230.94. ZP, Z per phase, as per the given problem. R is 20, XL is 15I. So we know by Pythagoras theorem or by impedance triangle, ZP is given as square root of R square plus XL square. The substituting that we get ZP, that is the magnitude of the impedance per phase, is 25 ohms. Power factor, as we know the formula, it is cos of RP by, that is per phase resistance by per phase impedance, or P by S. So substituting the values of R, resistance per phase is 20, the total impedance per phase is 25. The magnitude of impedance per phase is 25 ohms. So substituting that we get the value as 0.8. And why do we call lagging? Because we know it is inductance. If it is capacitance, it would have been 0.8 lead. Now, so let's see what happens when the capacitance is not connected and what happens when capacitance are connected. So current per phase, VP by ZP, we get 9.24, and the power, the formula for power in a three-phase circuit is given as root 3 VLIL cos phi. So substitute. So now you can see we have calculated IP, but here we are substituting the same value, because as discussed earlier, we know that in star IP and IL both are same. So solving that, we get the real power as 5120 watts. So please remember that this P remains unchanged before and after power factor correction. So Q root 3 VLIL sin theta or sin phi. Substituting the values, we get. So remember this. So calculate what is theta. The theta is 36 point some change. So inverse of that, you get sine of the angle, you get 0.6. So the value of Q is 3840 kVAR. Sorry, it is 3.840 kVAR. Now, when the capacitance are connected in delta fashion or star, as I mentioned here in delta, they've not mentioned. Okay, as we are connected capacitances, they say the power factor should improve by 0.95. So from 0.8 to 0.95 it has to be improved. So then the new angle is 18.2. So I hope you can see here that this angle, because of this, cos of phi 1 is 0.8 and cos of this angle is cos of phi 2 is 0.95. So this angle is 18, this angle is 36 point some degrees. So as we have seen that VAR2 is nothing but P into tan phi 2, where P does not change as we have shown in the vector diagrams earlier. So the value of P is 5120 into tan of 18.2. We get the new VAR is 1.684 K. Okay, so the leading VAR supplied by three capacitances is VAR1 minus VAR2 is 2156. However, VAR supplied by each capacitance, this is the total VAR supplied. So for a three-phase circuit, we'll have three capacitance. So amalgamation of all the three capacitance, the value is 2156. So then what is the value of VAR supplied by each capacitance? So divided by 3, it is 719 VAR. So this is the value of reactive component of power supplied per capacitance. Now, so let's find the value of capacitance. So in delta connection, voltage across each capacitance will be 400 as it's connected across the supply. So we know by Ohm's law that I is equal to P by V, right? I is equal to, or we know the power is simply I into V. This is the power, this is I, and multiplied by V, we get its reactive power, right? Not by Ohm's law, I'm sorry. So IC is equal to 719 divided by 400, we get 1.798 amperes is the current consumed by each capacitances. So also we know that IC is equal to, now this is by Ohm's law, that IC is equal to V by XC, and we know the value of XC as 1 by 2 pi FC. So from this equation, that is IC is equal to V by 1 by 2 pi FC, we'll find what is the value of capacitance. So simplifying this equation, we have this equation as this goes to the numerator. Now solving this, we get the value of capacitance as 14.32 microfarads. However, for a single phase, when you solve this problem, it's a balanced circuit. So in theory class, you'll be understanding the difference between balanced and unbalanced circuit. I'll restrict my explanation with respect to this experiment. So under a balanced circuit, we can solve the entire problem of a three-phase in as a single phase. Thus, when we do so, at that time the value of capacitance, we have to take the voltage as phase voltage, that is 230.94, and at that time the value of current, the value of capacitance is 49.5896 microfarads. So this is the value of capacitance for three phase, this is the value of capacitance for single phase. So we'll solve both and let us see the same in terms of simulation. So let us simulate the problem. So I hope now you are well versed in building the circuit. So I have built the circuit just to save time. Let me explain. So we take and revalue the value of resistance to 20. We take the value of L and we find out the value of L. So please understand the given value of XL is 15. So we have to find out the value of L. So as we are aware that the value of, that is, we are aware that XL is equal to omega into L. So this is nothing, omega is nothing but 2 pi into F. So we have to calculate the value of L for simulation. So we know the value of XL, we know the value of pi, we know the value of frequency 50, then you have to calculate the value of XL. So calculating the value of XL, calculating the value of L from the known value of XL is 47.7465 milli, right? And this is actually VAC, as you can see here, it is VAC. So what all parameters you have to set here? So since we are solving it for single phase, so the magnitude of per phase voltage is 230.94. and then no angles. Then, so as you are aware, this is I print now, and the output value is AC component. We need to see in terms of polar form, thus magnitude is typed as yes, phase is also typed as yes. And this you are connecting to find the voltage drop across the supply. So it's an AC component, magnitude is yes, phase is also being given yes. So that means we are seeing the outputs with respect to polar form in terms of magnitude and angle. Next, go to setup analysis, enable AC sweep. In that, the number of points that we want to see is only one value of current or voltage. At what frequency? At 50 Hertz. Thus the start and end frequency remains same. So do not enable, transients is not required, AC sweep is sufficient. And then we click on simulate. We get the output window. Go to view. So this window appears blank because we have not connected any probe. As we've connected a print, I print and V print, it prints the value. So go to view, output files, come down. This is for voltage. You can see the frequency is 5.0 to the power of e power 1, that is 50 ohms, 50 hertz. This is 2.309 e power 02, that is 230. And you can see the angle is mentioned as 0. And here we have for current, frequency remains same, that is 5.0 e power 1, that is 50. This is the value of, this is the magnitude of current, 9.238, and this is the angle before power factor correction. So you can see angle between voltage and current. So voltage is taken as x-axis, it is 0, and current is lagging by an angle of 36.87. So it is e power 01, that means it is 36. So the angle is minus 36.87. Okay, so this is cos of this will give us power factor, which is nothing but 0.8. Let's try to correct by adding a capacitance. The circuit is already built, so let me open that circuit. So what you have to do is add the capacitance for a single phase value you have calculated as 49.589 micro. So U stands here for micro. So I print it is same. So what you have to do is only add a capacitance here and then run the simulation. It is for AC. Go to view, output file. This, you can see the magnitude of total current now has been reduced from 9 point, what is the value of current here? You can see the value of current from 9.238 it is reduced to 7.642, and the power factor, you can see the angle was from minus 36.8, it has reduced to minus 14.74, right? And then cos of minus 14.74 is giving us as 0.967. So the design value was actually for 95. We're getting slightly higher because it's simulation without any losses, right? So this is with respect to single phase. The same thing can also be executed with respect to three phase. So let me open the file. So this is a circuit that we have to build. So we have three phase circuits. We'll have 3 resistance and 3 inductance. This value of inductance is for single phase, right? So as they said, it is in star connected. You can see all the ends are connected to ground, and this is the supply. Again, this is VAC as shown earlier, VAC. As we know, per phase angle differs by 120 degree. So this is magnitude of 400, phase angle of 0. This is again magnitude of 400 but angle of minus 120. This is again magnitude being 400 but angle being plus 120. Thus this is the 3 phase. Now why we have connected resistance? Because it says it's in a, you cannot connect voltages in a loop. it will not execute. So it should have a small resistance connected showing the losses, right? So I've just connected a small resistance in series of 0.1 micro ohms. Next, connecting them to respected, I've labeled as R, this as Y, and this as B. So connecting from each end to the load, and I'm connecting this V print with respect to, as we are aware, with these parameters parallel to one of the voltmeter, one of the phase, and this is to measure the line current. And go to setup analysis, it remains same, enable AC sweep. So as we simulate, so go to view, output file. Now this is the value of current that we got. Even for single phase it is same, it is 9.32. Now you can see here we are getting the angle before power factor correction is minus 66.87. So we are aware that between line and phase it deviates by 30 degrees. So what we have to do is reduce it by 30 degrees, that is minus 30 degrees, that is 66.87 plus 30 will give us the angle as minus 36.87, which is as same as what we had got for single phase. Minus 36.87 for single phase, minus 36.87 for three phase. This is before power factor correction. Okay, now let's see what happens after power factor corrections. So after power factor corrections, let me open the file. So you can see the same circuit. We have three capacitances of the value that we had calculated as 14.32 microfarads connected in delta fashion. So from each end it's been connected to your capacitance and measuring current and voltage. So setup analysis, it is AC sweep, it remains same, linear, total points 1, start and end frequency remains 50. So let us simulate. Let us go to view, output file. Now, so you can see here the current is reduced to 7.778. So whereas, so here it is 7.778 after power factor correction, whereas in single phase it was 7.642, a small deviation. And then the angle that we had got, this is after this is before, what we had got was 14.74. So let us see what is the angle here. Right, so as discussed earlier, so this is minus 48.17 plus 30, which is equal to 18.17, and then cos of minus 18.17 is equal to 0.95. So this is the power factor that we had desired, whereas in single phase we're getting slightly higher, that is 0.967, but under three phase we're getting accurately. Okay, so this is how one has to verify the theoretical calculations over PSpice. So once we have done, so this is the value of capacitance chosen for three phase, this is the value of capacitance that we have chosen for single phase. So that we have done the simulation. Remember, any lab, if you are working on a hardware, please get it inspected first, by lab instructor or faculty, before you energize. So thank you for watching the video. Please do subscribe the YouTube channel to enhance your knowledge further.